Hello everyone, welcome to Statistical Methods. In this video we'll be talking about empirical risk minimization and the James-Stein estimator. And basically this is a way to estimate the hyperparameter in linear shrinkage. If you'd like to study this yourself, then go to the lecture notes in the chapter 11. And so let's get started. So let's recall the thing that we observed in all the three models we've discussed so far. So this was called linear shrinkage. So we had a parameter theta that we would like to model, and we had a theta hat ML, which was our likelihood estimate. We had theta naught, which was our prior mean. So this was the likelihood estimate, so maximum likelihood estimate, and we got as posterior mean, so we call this post, was the expectation of theta given the data x1 to xn, and that was the convex combination of theta naught plus 1 minus lambda. Theta had ml and lambda was between 0 and 1. And when lambda is close to 1, then theta posterior will be the prior, and so let's remove the hat inconsistent. So, and if there's no shrinkage, then lambda post will be the maximum likelihood estimator, so no shrinkage. Here we have full shrinkage. So that's the idea. And so this thing is also called the target. So this is the target. And usually, so in base, lambda is given by something like m divided by m plus n, so with m given. So m is a hyperparameter, so that's specified in advance. So that's good and that's bad in a way, because we need to, sometimes we actually don't want to specify this. So we obviously n is fixed, so this is our actual sample size, so that's data, and the m is related to the how concentrated the prior is. So how concentrated is your prior, and if it's precise, if you have a precise prior, m is large, and if you have a vague prior, m is small. So the question is, and that's ideas, can we actually learn, lambda itself from the data? And this idea can be answered positively. So, and this leads to the idea of empirical risk minimization. And also links with empirical base. So this empirical means we actually use data to determine the hyperparameterization. So use data to determine hyperparameters. And intriguingly, this also leads to a link between base and frequentist. Test methods, because we're using frequentist method to estimate a Bayesian quantity. So the basic idea is we look at the true value, so theta is our true value now, and we'd like to minimize the MSE. So we take the shrinkage estimate or the posterior mean, and we take the squared error from the true mean and then the expectation and try to minimize this. Try to minimize lambda, or try to minimize this quantity to get lambda. So that sounds weird, but it turns out that it's actually possible. So it sounds weird because we don't know. So this is unknown. But it turns out that if theta hat ml is unbiased, if theta hat ml is unbiased, then the optimal value of lambda is the following. So optimal value of lambda, so we call this lambda star, is the ratio of the variance of the maximum likelihood estimator divided by something called basically the fit or misspecification between the maximum likelihood and the prior. So, and that's the interesting point here. So we have a variance of ml e, and that becomes small with n. So the larger n, the smaller this becomes. And this thing here is the misspecification between prior and MLE. So if, so this is large if prior is too far away from MLE, which is good because the MLE is what we get from the data. So if the prior is too far away, lambda is small, so lambda star small if n large, or prior is likely to be incorrectly chosen, because if it's too far away, then the data, if prior contradicts data. So that is the idea. So you can find expressions of the optimal intensity in terms of the variance of the maximum likelihood and the misspecification of the prior and the maximum likelihood estimator. And a famous example of this is the James-Stein estimator. So the James-Stein estimator is an example. So James-Stein, that is from 1955, and that actually created a big startup, a big controversy, because at this point everybody still believed that maximum likelihood is the best method available, and they showed that you can actually beat maximum likelihood. So the idea was, we have x, so is drawn from a multivariate normal with some mean mu and the identity matrix. So we have basically d samples, x1, xd from 0, 1, from mu I and 1. So the mu I is, the mu is mu 1 to mu d. And the question is how to estimate mu. And it turns out so that the MLE is mu hat ML is x, so without bar, because there's only one sample, so single sample. And if we do the shrinkage intensity, lambda star equals to d minus 2 divided by the misfit. So this is actually the estimator of the, this is exactly this formula as above here, where you divide the variance divided by the difference between the mean and the target. So in this case the target is 0, so we use mu naught zero. Then we get as James-Stein estimator the following. Mu hat James-Stein is 1 minus lambda, so in this case d minus 2 divided by the sum of squares of the x times x. So this is the mu hat ml 1 minus lambda, and because we also have lambda times mu naught, but mu naught is 0, so this is why we just remove this part. But so this is the James-Stein estimator, and the key thing is that for all x, the MSE of mu hat James-Stein is by construction smaller than that of mu hat ml, which means that the James-Stein estimator is called dominates the ml estimator. And this is what was the puzzling thing. So you can actually choose the maximum likelihood estimator and the not the maximum, you can choose the lambda in the shrinkage estimator, so that the shrinkage estimator is always better than the maximum likelihood estimator. So you can choose, and that's the thing, automatically and data adaptive, that's how you call this nowadays, because this is just the very first, very simplest method. Data adaptive, the shrinkage intensity and outperform the MLE in terms of mean squared error. So obviously for large samples both converge. For large samples James-Stein converges to ML, but for small n is better than the ML. So that's the puzzling thing. So in traditional Bayes you fix the sample size or the precision of the prior in advance, and in this setting, in the empirical risk estimation setting, you can use an external criterion, in this case the mean squared error, to choose the hyperparameter. So use risk optimization to select optimal hyperparameter, and this is then called empirical Bayes. So there are several ways to do this. So you can use the marginal likelihood, or you can use MSE, or you can use many other things, but the whole idea is you have 3 parameters in your prior and you choose those 3 parameters using the data itself. So that's it for today. So hope you enjoyed the Bayesian statistics so far, and then see you next week in the next videos. Until then, bye bye.